There exists within the cosmos something that should not be there. Not in the way we understand the universe to be assembled, not according to the elegant mathematics that we have laboriously written to describe the behavior of all things great and small. And yet it is there, vast beyond human comprehension, a structure so immense that light itself, traveling at the fastest speed possible in this universe, would require billions of years to cross from one end to the other. This is the story of that impossible thing, and in learning of its existence, we will come to understand something profound about the nature of reality itself and about the ongoing process of scientific discovery. The exploration of the cosmos has always been one of humanity's greatest endeavors. From the time when our ancestors first learned to wonder about the stars that filled the night sky, to the modern era in which we possess instruments capable of peering across billions of light-years of space, the impulse to understand the universe has been a defining characteristic of human civilization. We have built temples to observe the heavens. We have developed mathematical systems to describe the motions of the planets. We have created increasingly sophisticated instruments to gather light from distant objects. And through all of these efforts, we have gradually expanded our understanding of the cosmos and our place within it. But understanding something as vast and as complex as the universe is not a simple matter. It requires not just better instruments and more observations, though these are certainly important. It also requires careful thought about what we are observing, about how we interpret the data that our instruments provide, about how we construct theories to explain what we see. It requires an ongoing dialogue between observation and theory, between what we measure and what we understand. When these two agree, we are confident that we are on the right track. But when they diverge, when observation reveals phenomena that theory cannot explain, that is when the most important work begins. The cosmos presents itself to us in a way that is both accessible and deeply mysterious. We can observe it. We can collect light from distant galaxies and analyze its properties. We can measure the positions and distances of billions of stars and galaxies. We can compile this information into maps and models that represent our understanding of the universe's structure and composition. And yet, for all of this information, for all of the data that we have gathered, there remain aspects of the universe that we do not understand. There are mysteries that persist. There are phenomena that do not fit neatly into our existing categories of understanding. And it is in these mysteries and these gaps between what we observe and what we can explain that the frontier of science exists. One of the most remarkable mysteries of this sort, one of the great puzzles that has occupied cosmologists in recent decades, concerns the existence of structures in the universe that appear to be larger than they should possibly be. According to our current understanding of how the universe evolves, according to the mathematical models that we have constructed based on our knowledge of gravity and the behavior of matter on large scales, certain structures should not exist. And yet they do exist. They are observed. They have been measured and characterized in detail. And their existence presents a challenge to our understanding that we are still working to resolve. When we look up at the night sky with our eyes alone, we see points of light arranged in patterns that our ancestors named and told stories about for countless millennia. We saw bears and hunters, warriors and mythical beasts painted across the darkness by stars that seemed eternal and unchanging. It was a comfortable view of the universe, one that placed humanity at the center of all things, surrounded by a vast but comprehensible cosmos. We now know that this intuitive understanding, beautiful though it is, represents perhaps the smallest fraction of what actually exists around us. The universe is far stranger, far more elaborate, and far more wondrous than we could have imagined when we were merely gazing upward from the surface of our small world. In the 20th century, human civilization achieved something remarkable. We developed tools and techniques that allowed us to see deeper into the universe than any previous generation had done. We built telescopes that could gather light from objects so distant that the photons entering our instruments had been traveling through space since before our species had learned to walk upright. We learned to analyze that light with mathematical precision, to read the stories it contained about distant galaxies, about the chemical composition of the universe, about its structure and its age and its fate. These tools and this knowledge represented a kind of expansion of human consciousness itself, a way of extending the reach of our senses far beyond the biological limitations we inherited from our evolutionary past. But even as we peered deeper, we organized the universe in our minds according to a certain hierarchical scale. There were individual stars, like our own sun, burning bright in the darkness. There were galaxies, vast assemblies of billions or trillions of stars held together by their mutual gravity, rotating majestically through space. And there were galaxies gathered together into groups and clusters and superclusters, all bound together by gravity, all settling into a cosmic web of matter separated by vast voids of emptiness. This structure seemed logical, comprehensible, a natural hierarchical organization that extended from the smallest scales we could measure to the largest. It seemed that we had finally grasped the basic architecture of existence. In this cosmic web, galaxies are not arranged randomly. If you were to somehow leave the surface of our planet and travel upward, accelerating faster and faster until you could see our entire solar system as a small thing, then accelerating further still until our galaxy appeared as merely one among many, you would begin to notice that the galaxies around you are not distributed evenly through space. Some regions are crowded with galaxies, bright and dense, while others are almost empty. The galaxies tend to gather along what appear to be filaments, long thin structures along which galaxies accumulate like beads on a string. Between these filaments lie vast voids, regions of emptiness many millions of light years across where few galaxies dwell. These filaments and voids became known as the cosmic web, and for many decades it seemed that this represented the largest scale of structure in the universe. The galaxies clustered along filaments, the filament threaded through the voids, and if you looked at a large enough scale, the universe would appear roughly homogeneous and isotropic, meaning that it would look much the same from any direction and from any vantage point. This was consistent with the cosmological principle, an assumption that has underlaid most modern cosmology since the early 20th century. The cosmological principle states that the universe, on sufficiently large scales, appears the same everywhere. There are no special locations, no center, no edges. Just an infinite or near infinite expanse of space populated roughly equally with matter and energy. This principle was deeply satisfying to physicists and astronomers, and it had proven remarkably accurate. It allowed us to write down the equations that describe the evolution of the universe as a whole, to understand how it began in the Big Bang, and how it has expanded and cooled over nearly 14 billion years. It explained the cosmic microwave background radiation, the remnant thermal radiation from the early universe that we can still detect today, bathing us in light that has been traveling through space since the universe was less than 400,000 years old. The cosmological principle seemed to be one of the great truths about the universe, a fundamental symmetry upon which all of modern cosmology rested. But there is something deeply human about our need to organize our understanding into clean categories and simple principles. We take comfort in symmetry and in the sense that we have grasped something essential. And often, when we are most confident in our understanding, the universe offers up a surprise, a discovery that forces us to reconsider everything we thought we knew. This is exactly what happened with the discovery of structures that should not exist, structures so large that they challenged the very foundations of our understanding of cosmic structure formation. In the early years of the 21st century, astronomers and cosmologists were engaged in a massive project to map the universe in 3 dimensions. They were using a large telescope in New Mexico called the Sloan Digital Sky Survey, which could observe hundreds of thousands of galaxies and measure their distances from us with remarkable precision. The technique they employed was elegant in its simplicity. Light from distant galaxies contains the signatures of the chemical elements within them, specific wavelengths of light that are absorbed or emitted by different atoms. But because the universe is expanding, this light is stretched and shifted as it travels toward us, a phenomenon known as the redshift. By measuring this redshift, astronomers could determine how far away each galaxy was. Redshift, in a sense, is a cosmic yardstick. As they compiled their data, astronomers began to notice something unexpected. There appeared to be a massive structure, far larger than anything they had thought could exist. It was a wall of galaxies, stretching across billions of light years, a vast flat sheet of matter embedded in the cosmic web like an enormous canvas painted on the darkness. They named it the Sloan Great Wall, after the telescope that had revealed it. But there was something troubling about this discovery. According to all of their theories, according to the mathematical models that had served them so well for decades, such a structure should not exist. It was too large, too regular, too impressive at its scale. To understand why this was troubling, we must understand something about the timeline of the universe and the growth of structures within it. In the beginning, shortly after the Big Bang itself, the universe was extraordinarily smooth and homogeneous. The early universe was hot and dense and essentially featureless. But it was not perfectly smooth. There were tiny fluctuations in density, random variations of perhaps 1 part in 100,000. These fluctuations were almost impossibly small, yet they held within them the seeds of all future complexity. As the universe expanded and cooled, gravity began to work upon these tiny variations, pulling material together into denser regions and creating more pronounced contrasts between dense and less dense areas. This process of gravitational growth of structure is not instantaneous. It takes time. The universe has been expanding and cooling for nearly 14 billion years, and the largest structures we see today represent the accumulated growth of gravity working on these seed fluctuations across that entire span of time. According to the detailed calculations that astronomers have performed, the largest structures that could possibly have formed in this amount of time should be perhaps a few 100 million light years across. The Sloan Great Wall, stretching across more than 1 billion light years, seemed to exceed these theoretical predictions. It was too large for the time available. It should not have had time to grow to such a size. It represented a fundamental challenge to our understanding of cosmic structure formation. And yet, as astronomers continued their observations, and as more and more data accumulated, they discovered that this was not an isolated anomaly. Other massive structures began to emerge from the data. There was the Hercules supercluster, another vast accumulation of galaxies spanning hundreds of millions of light years. There was the Great Wall of Hercules and Perseus, and the Pisces-Cetus supercluster, an enormous structure of matter more than 1 billion light years across. These discoveries suggested that something was fundamentally wrong, not with the observations themselves, but perhaps with the theoretical framework that astronomers had constructed. The implications were staggering. If these structures truly were as large as they appeared to be, then either the universe was much older than we believed, giving gravity more time to work, or the structures had somehow formed in ways that we did not yet understand. The universe was not on the verge of revealing some simple secret. Rather, it seemed to be indicating that our comprehension of it remained incomplete. We had peered into the cosmos with our instruments and our mathematics, and we had found evidence that the cosmos was more subtle and more complex than we had appreciated. As astronomers studied these structures more carefully, they began to compile a more detailed picture of the universe's large-scale architecture. What emerged was something both beautiful and strange. The universe on the largest scales is not a random or featureless place. It is, instead, a vast cosmic city of structures, vast filaments of galaxies stretching across billions of light years, separated by enormous voids that are nearly empty of matter. The filaments themselves are often studded with knots and nodes, regions of even greater density where multiple filaments intersect, and where the greatest concentrations of galaxies accumulate. This cosmic web is the largest structure visible to us, and it extends as far as our telescopes can reach. But among these structures, certain ones stood out as being particularly large and particularly problematic from a theoretical perspective. The Sloan Great Wall remained one of the most impressive. Yet as observations continued and improved, as the universe map became more detailed and more comprehensive, astronomers began to debate whether the Sloan Great Wall was truly a single unified structure, or whether it might be a collection of smaller structures that merely appeared connected when projected onto a two-dimensional map. But this debate, while important for understanding the precise nature of the structure, did not resolve the fundamental problem that it represented. Structures this large should not exist, at least not according to our conventional understanding of how the universe evolves. This brings us to one of the most profound questions in modern cosmology, a question that has occupied the minds of researchers for decades, and that remains only partially answered. How can we reconcile our theoretical understanding of structure formation in the universe with the observational reality that these enormous structures appear to exist? There are several possible resolutions to this puzzle, and they each carry profound implications for how we understand the cosmos. One possibility is that our measurements of cosmic distances, our redshifts, and our standard candles, and our yardsticks, are somehow systematically wrong in a way that we have not yet recognized. Perhaps the structures appear larger than they really are due to some subtle error in our methods. But this seems unlikely. These techniques have been tested extensively, cross-checked against multiple independent methods, and verified against other observations. The redshift measurements are particularly robust, supported by decades of observations, and by detailed understanding of the physics involved. Another possibility is that the structures are indeed as large as they appear, but that they formed in ways we do not yet understand. Perhaps there are mechanisms of structure formation that we have overlooked, processes that could accelerate the growth of large-scale structures and allow them to reach such tremendous sizes in the time available. This possibility has led to extensive theoretical work, with cosmologists exploring alternative scenarios and mechanisms that might explain what we observe. Some have looked to modifications of gravity itself, to the possibility that on the largest scales, gravity might behave differently than Einstein's general relativity predicts. Others have explored the role of dark matter and dark energy in greater detail, searching for ways that these mysterious components of the universe might drive structure formation more efficiently than current models suggest. The third and perhaps most sobering possibility is that our understanding of the timeline of the universe itself is wrong. We believe the universe is nearly 14 billion years old, based on observations of the cosmic microwave background radiation, on measurements of the expansion rate of the universe, and on studies of the oldest stars and globular clusters we can observe. But what if this age estimate is significantly wrong? What if the universe is substantially older than we believe? In that case, gravity would have had more time to work, and larger structures could have formed naturally. The implications of this possibility are profound, for it would mean that our understanding of one of the most fundamental properties of the cosmos is significantly mistaken. As we contemplate these possibilities, we must remember that science is not a collection of final truths, but rather an ongoing process of asking questions and testing hypotheses against the evidence that the natural world provides. In this spirit, let us turn our attention back to the structures themselves and consider them not merely as problems to be solved, but as wonders to be understood and appreciated. The largest structure that we know of in the universe that poses this theoretical challenge is sometimes called the Hercules supercluster, though the naming of cosmic structures is a somewhat arbitrary affair, and different astronomers sometimes use different names for the same regions of space. This vast structure stretches across distances that are almost impossible for the human mind to fully grasp. If you were to travel at the speed of light, the fastest possible speed in the universe according to Einstein's theory of relativity, it would take you more than 500 million years to traverse this structure from one end to the other. Let us for a moment contemplate that number. The fastest conceivable journey, impossible though it is, across the breadth of a single cosmic structure would consume a period of time longer than the entire history of complex life on Earth. The dinosaurs, those remarkable creatures that dominated our planet for more than 100 million years, would seem like a brief flash, a momentary spark of existence, compared to the time required to cross this single structure. When we attempt to visualize such scales, we are forced to confront the essential inadequacy of human intuition. Our brains evolved in an environment where the largest distances we needed to navigate were a few hundred meters, the distances across our ancestral landscape. We hunted and gathered and lived out our lives within territories measured in miles, or at most dozens of miles. Our intuition about space and distance, about what is large and what is small, was calibrated to these scales. When we are asked to contemplate structures spanning billions of light years, we are being asked to extend our comprehension far beyond anything that natural selection could have prepared us for. And yet, through the combination of observation and mathematics, we have managed to grasp something of what is happening on these scales. We have built telescopes and set robots into space to gather information about the distant universe. We have developed the mathematics of general relativity to describe how gravity operates across cosmic scales. We have written down the equations that describe the behavior of the expanding universe itself. In this way, we have achieved something remarkable. We have, in a sense, extended our senses far beyond their natural limits. We have used our brains and our tools to perceive things that no human eye could ever see, to understand places that no human being could ever reach. Now, as we study these vast structures, we begin to notice something else that is quite remarkable. The structures do not appear to be distributed randomly through space. Rather, they seem to follow a certain pattern, a certain organization. The filaments, those vast threads of galaxies, seem to intersect in ways that create a network, a web-like structure of matter separated by voids of emptiness. Moreover, the density fluctuations between the densest regions and the emptiest regions, while certainly present, are not as extreme as we might have expected. The universe is lumpy, but not wildly so. There is structure, but the structures do not dominate completely. This hints at something important about the early universe and about the nature of the processes that led to the existence of these structures. To truly appreciate the magnitude of the challenge these structures present, we must understand in greater detail the observational methods by which we have come to know of their existence. The process of mapping the universe and discovering these vast structures represents one of the great achievements of modern astronomy, an accomplishment that required the development of new technologies, new analytical techniques, and the sustained effort of thousands of researchers working across many decades. In the early 20th century, the largest telescopes could only measure the positions and brightnesses of stars and nearby galaxies. The universe, as viewed through these instruments, appeared to be a relatively simple place, with galaxies scattered apparently randomly through space. But as telescopes improved, as the technology advanced, as new methods of measurement were developed, astronomers began to see deeper into the cosmos. The development of the spectroscope, an instrument that breaks light into its component wavelengths, allowing us to identify the chemical composition and the motion of distant objects, was revolutionary. The spectroscope made it possible to measure the redshift of distant galaxies, and thus to determine their distances. With this technique in hand, astronomers could for the first time build three-dimensional maps of the universe, plotting the positions of galaxies not just in 2 dimensions on the sky, but also mapping their distances from us. In the late 20th century, the technology reached new heights with the development of large, automated telescopes equipped with sensitive detectors called charge-coupled devices, or CCDs, which could record faint light with remarkable efficiency. These new instruments, combined with advances in computer technology that allowed for the processing of enormous quantities of data, made it possible to measure the redshifts of thousands, and then tens of thousands, and eventually hundreds of thousands of galaxies. These large redshift surveys provided data on an unprecedented scale, revealing the structure of the universe in 3 dimensions with clarity that had never before been possible. The Sloan Digital Sky Survey, which we have mentioned several times already, was perhaps the most ambitious such project. Beginning in the year 2000 and starting with the telescope in New Mexico, it systematically surveyed a large portion of the sky, measuring the positions and redshifts of hundreds of thousands of galaxies. This project, which continued for many years and produced an enormous archive of data, fundamentally changed our understanding of the large-scale structure of the universe. It was the data from this survey that revealed the Sloan Great Wall and highlighted the puzzles that we have been discussing. The process of analyzing such vast datasets required the development of new statistical and computational methods. Astronomers needed to develop techniques for identifying structures within the data, for distinguishing genuine structures from artifacts or statistical fluctuations, for measuring the properties of structures precisely and reliably. This work was painstaking and required careful attention to detail, to understanding the sources of error and uncertainty, to avoiding the temptation to see patterns that might not be there. It represented a kind of detective work, a systematic search for the truth hidden within vast mountains of data. One of the key innovations in this work was the development of algorithms for identifying voids and filaments in the galaxy distribution. Unlike stars within a galaxy or galaxies within a cluster, which are bound together by gravity and form coherent structures, the filaments and voids of the cosmic web are more subtle. They represent regions where the density of galaxies is slightly higher or lower than average, but the boundaries are fuzzy and the structures are not sharply defined. Identifying and characterizing these structures required the development of sophisticated mathematical techniques, algorithms that could recognize patterns in the data while remaining sensitive to the genuine structures and resisted to noise and statistical fluctuation. These techniques have proven remarkably successful. By applying them to the data from large galaxy surveys, astronomers have been able to map out the large-scale structure of the universe in unprecedented detail. They have identified the positions of the major superclusters, traced out the filaments along which galaxies preferentially accumulate, and measured the sizes and properties of the voids between them. The result is a 3-dimensional map of the universe that is both beautiful and revealing, showing the cosmos as a vast cosmic web of matter threaded through space. But the discovery of these structures also brought with it a new set of challenges. As we have discussed, the structures that were discovered appeared to be larger than the available time would have allowed to form. This raised fundamental questions about the completeness and correctness of our understanding of cosmic structure formation. It forced cosmologists to reconsider their assumptions, to examine their models more carefully, to consider whether modifications or revisions might be necessary. The response from the theoretical community has been vigorous and multifaceted. Teams of researchers around the world have been working to understand how these large structures could have formed. They have conducted increasingly detailed simulations of the evolution of the universe, following the growth of structures from tiny seed fluctuations to the present day. They have explored modifications to the standard model of cosmology, considering alternative physical processes that might affect structure formation. They have analyzed the observational data in ever greater detail, looking for possible systematic errors or reinterpretations that might resolve the tension between theory and observation. One particularly important avenue of investigation has involved more careful analysis of whether the structures we observe are truly as large as initial readings of the data suggested. This work has required careful statistical analysis, taking into account the uncertainties in distance measurements, the subjectivity of structure definitions, and the possibility of observational biases. Different research groups, using different methods and different definitions of what constitutes a structure, have obtained somewhat different results. Some have found that the structures are slightly smaller than earlier studies suggested. Others have confirmed the earlier measurements. Still others have proposed that the apparent structures might be somewhat artificial, products of the particular way that the data is analyzed or visualized rather than genuine cosmic structures. But despite these refinements and reanalysis, the core puzzle remains. There are definitely large structures in the universe, structures spanning 1 billion light-years or more. Whether or not these structures are quite as large as the most dramatic initial report suggested, they remain problematically large from the perspective of standard cosmological models. The fact that they exist, and that they appear to approach the theoretical limits of how large structures could possibly be in the time available, continues to pose a challenge to our understanding. This is a healthy situation from the perspective of science. The presence of this puzzle, the existence of this tension between observation and theory, provides motivation for further research, a reason to look more deeply, to think more carefully, to develop new insights and new understanding. Without such puzzles, without such challenges, science would be in danger of stagnation, of settling into comfortable certainties, and ceasing to question and investigate further. When we look at the cosmic microwave background radiation, the remnant thermal glow from the early universe, we find that it too possesses a certain structure. It is not perfectly smooth. There are tiny variations in temperature from place to place, regions that are slightly warmer or slightly cooler than the average. These temperature variations correspond exactly to density variations in the early universe, to those seed fluctuations that we discussed earlier. By studying the pattern of these temperature variations, by measuring their amplitude and their distribution across different scales, astronomers have been able to infer a great deal about the composition of the universe and the physical processes at work in its first few 100,000 years of existence. What emerges from these studies is a picture of the early universe that is quite interesting. The universe was not smooth, but it was remarkably uniform. The variations in density were small, typically only a few parts in 100,000. But these variations, seeded perhaps by quantum fluctuations in the first fraction of a second after the Big Bang itself, contain the blueprint for all future complexity. They contain the seeds from which galaxies and stars and planets, and eventually life would grow. In the course of the past 14 billion years, gravity has amplified these tiny variations into the vast structures we see today. But here is the puzzle. The calculations show that, starting from the magnitude of the variations we observe in the cosmic microwave background, and given the amount of time available since the Big Bang, the structures that form should be somewhat smaller than what we actually observe. The theoretical predictions and the observations do not quite match. The universe appears to have grown its structures more quickly or more efficiently than the standard models predict. This discrepancy, small though it might be in percentage terms, becomes significant when we are considering timescales of billions of years and structures spanning billions of light years. Small differences in growth rates, compounded over such vast stretches of time and space, can lead to substantial differences in the final size and complexity of the structures produced. One avenue of exploration that has occupied cosmologists in recent years is the question of whether dark matter, the mysterious substance that comprises the vast majority of the matter in the universe, might play a more active role in structure formation than previously appreciated. Dark matter is called dark because it does not emit, absorb, or reflect light. We cannot see it directly. We know it exists only because of its gravitational effects, because we observe that galaxies rotate too fast for the amount of visible matter that they contain, and because we see the gravitational effects of dark matter in the way that light is bent as it travels through the universe. Yet we do not know what dark matter actually is. It does not consist of atoms and molecules as we understand them. It is not made of the familiar protons and electrons and neutrons that make up all the ordinary matter in the universe. What dark matter might be made of remains an open question in physics, one of the great mysteries of our time. Some theorists believe it consists of exotic particles that were created in the early universe, but that rarely interact with ordinary matter except through gravity. Others have proposed different solutions, different ways of understanding gravity itself that might eliminate the need to invoke dark matter at all. But regardless of its nature, dark matter clearly plays an enormously important role in the structure and evolution of the universe. If we were to remove all the dark matter from the universe, galaxies would fly apart, and the universe would be transformed beyond recognition. In the early universe, dark matter would have begun to accumulate in regions of slightly higher density, pulled together by its own gravity. These accumulations of dark matter would have formed what are sometimes called dark matter halos, vast spheres of invisible matter surrounding and permeating the regions where galaxies would eventually form. The ordinary matter, made of atoms and capable of radiating heat and light, would have then accumulated within these dark matter structures, eventually condensing into galaxies. In this sense, dark matter provided the scaffolding upon which all visible structure would be built. The implications of this puzzle about the existence of structures larger than theory predicts extend beyond the immediate question of cosmic structure formation. They touch on deeper issues about the fundamental nature of the universe, about the laws of physics that govern its behavior, and about the initial conditions from which everything evolved. If the structures truly are as large as observations suggest, then something about our understanding is incomplete or incorrect. It might be that we have misunderstood how gravity operates on the largest scales. It might be that there are forms of matter or energy in the universe that we have not yet recognized. It might be that the initial conditions of the universe were different from what we have assumed. It might be that time itself, or the relationship between time and the expansion of the universe, is different from what our models suggest. Each of these possibilities, if true, would have profound implications for physics. A modification of general relativity on large scales would shake the foundations of modern physics, and would open up new avenues of investigation. The discovery of a new form of matter or energy would be equally revolutionary. A change in our understanding of the initial conditions of the universe would require us to reconsider the theory of cosmic inflation, one of the cornerstones of modern cosmology. and a revision to the relationship between time and cosmic expansion would fundamentally alter our understanding of the nature of time itself. It is precisely these kinds of challenges, these moments when observation meets theory, and they do not quite align, that drive science forward. These are the moments when genuine discovery becomes possible, when we are forced to think in new ways, to venture into new territories of thought, to question assumptions that we might otherwise have taken for granted. The history of science is replete with examples of such moments leading to profound discoveries and fundamental insights. Consider the development of quantum mechanics in the early 20th century. Classical physics, based on the equations of Newton and refined by Maxwell and other 19th century physicists, seemed to be a complete and adequate description of the natural world. But detailed observations of how light interacts with matter, observations of atomic spectra, observations of the behavior of electrons in different environments, revealed phenomena that classical physics could not explain. These discrepancies between observation and theory led to the development of quantum mechanics, a revolutionary new framework for understanding the behavior of matter and energy at the smallest scales. Quantum mechanics not only resolved the puzzles that classical physics could not explain, but it opened up entirely new fields of investigation and led to practical applications that have transformed human civilization. Or consider the development of general relativity. Newtonian gravitation, developed in the 17th century, seemed to provide a complete and adequate description of how gravity operates. It explained the motions of the planets, the behavior of the tides, the trajectories of projectiles. But careful astronomical observations, particularly observations of the orbit of Mercury, revealed small discrepancies between the predictions of Newtonian gravity and what was actually observed. These discrepancies were tiny, barely noticeable, yet they could not be explained away. In attempting to resolve them, Einstein developed the theory of general relativity, which revealed gravity to be not a simple force pulling objects together, but rather a curvature of space-time itself caused by the presence of matter and energy. This new understanding of gravity opened up entirely new vistas, leading to predictions of black holes and gravitational waves that were confirmed only decades later through observations. In a similar way, the existence of cosmic structures larger than theory predicts might be pointing us toward the next major advancement in our understanding of cosmology and fundamental physics. It might be that the resolution of this puzzle will require us to develop new theories, to refine our understanding of dark matter and dark energy, or to reconsider some aspect of the Big Bang and the origin of the universe. Whatever the case, the challenge posed by these observations is a gift to science, an opportunity to learn something new, to deepen our understanding, to move closer to comprehending the fundamental nature of reality. And as we work toward resolving this puzzle, as we make new observations, develop new theories, and test those theories against the evidence that nature provides, we are engaged in a process that is as old as human curiosity itself. We are asking questions about the world in which we live. We are seeking to understand the nature of reality. We are attempting to discern the patterns and principles that underlie the apparent diversity and complexity of the universe. This is the essence of science, the heart of the scientific endeavor, and it is one of humanity's most noble and most characteristically human activities. Now, some theorists have wondered whether modifications to our understanding of how dark matter behaves, or how it interacts with ordinary matter, might explain the existence of these unexpectedly large structures. Perhaps dark matter is not quite as smoothly distributed as we have assumed. Perhaps it tends to cluster more efficiently, or to grow its structures more quickly than our current models predict. Or perhaps there are subtle aspects of the dark matter distribution that we have not yet recognized or properly incorporated into our models. This remains an active area of research, and new observations and new theoretical insights continue to refine our understanding of the role of dark matter in cosmic structure formation. Another possibility that has been explored is related to the other great mystery in cosmology, dark energy. In the late 1990s, astronomers making observations of distant supernovae discovered something truly astonishing. The expansion of the universe was not slowing down as they expected. Instead, it was speeding up. Gravity, they had assumed, should gradually slow the expansion that had begun with the Big Bang. But instead, something was accelerating the expansion, pushing all of the galaxies away from each other with increasing force. This observation led to the introduction of dark energy into cosmological models, a mysterious form of energy that pervades all of space and that has the opposite effect of ordinary matter and energy, pushing outward rather than pulling inward. Dark energy comprises the vast majority of the energy content of the universe, roughly 70%. The rest consists of dark matter at about 25% and ordinary matter at about 5%. In other words, we can see only about 5% of what makes up the universe. The other 95% remains mysterious. Dark energy appears to be causing the expansion of the universe to accelerate, and in a distant future, many billions of years from now, it will likely dominate the behavior of the universe so completely that gravity will become entirely negligible. All galaxies will accelerate away from each other, all stars will eventually burn out, and the universe will become a cold, dark, and empty place, expanding forever into an infinite future. But dark energy is not only relevant to the far future. It also affects the growth of structures in the present and recent past. As dark energy becomes more and more important in driving the expansion of the universe, it makes gravity's job more difficult. Dark energy acts as a kind of cosmic repulsion, working against gravity's attraction. This means that the growth of structures slows down as the universe ages. The early universe, before dark energy had come to dominate, saw rapid growth of structures as gravity amplified the initial density variations. But in recent billions of years, as dark energy has increasingly taken over, the growth of structures has slowed considerably. Given these considerations, the existence of these enormous structures, these vast walls and filaments of galaxies spanning billions of light years, becomes even more remarkable. If structure growth has slowed in recent billions of years due to dark energy, then these structures must have grown to most of their present size in the earlier epoch, when dark energy was less important. This means that the growth of structures must have been quite efficient in the early universe, starting from the small seed fluctuations we observe in the cosmic microwave background and reaching the enormous scales we see today within a time frame that is increasingly seen as inadequate by many theoretical models. This brings us back to the central puzzle, the mystery that has occupied cosmologists for the past couple of decades. It is a puzzle that is not yet fully solved, and that likely will not be solved without new observations, new theoretical insights, or possibly both. The existence of these large structures challenges our understanding, and in doing so, it demonstrates one of the most beautiful aspects of science. When observation and theory diverge, when reality does not match our predictions, we are provided with an opportunity to learn something new, to revise our understanding, to approach the cosmos with fresh eyes, and with humility before its complexity and its beauty. Let us now turn our attention more specifically to one of these mysterious structures, to explore its properties and its place within the broader cosmic context. The structure that has received perhaps the most attention and the most detailed study is sometimes referred to as the Hercules supercluster, though as we have noted, The naming of cosmic structures is somewhat arbitrary, and different researchers sometimes use different nomenclature. This supercluster consists of a vast collection of galaxy clusters, the groupings of galaxy groups, the assembling of billions of galaxies into a structure so immense that the mind struggles to comprehend it. To understand the scale involved, let us consider what a single galaxy contains. The Milky Way, our own galaxy, contains somewhere between 100 billion and 400 billion stars, depending on which estimate one accepts. Most of these stars are quite small, red dwarf stars that are far less luminous and far less massive than our own Sun. But even accounting for the prevalence of these small stars, the total number of stars in the Milky Way is almost incomprehensibly large. If you were to count one star per second, without sleeping or pausing, it would take you tens of millions of years to count all the stars in our galaxy alone. And the Milky Way is not even an unusually large galaxy. In fact, it is a fairly substantial galaxy, but there are others in the universe that are far more massive and far more impressive. The galaxy M87, located in the Virgo cluster, is vastly larger than the Milky Way, containing perhaps over 1 trillion stars. The galaxy NGC 4889, located in the Coma cluster, is even more enormous. When we speak of a supercluster, we are speaking of a collection of many hundreds or thousands of such galaxies, each of which may contain hundreds of billions of stars. The total count of stars in a supercluster is a number so large that it is essentially no meaning to the human mind. It exceeds the total number of grains of sand on all the beaches of Earth. It exceeds the total number of snowflakes that have ever fallen in the entire history of our planet. It is a number that is nearly incomprehensible. And yet, when we view such a supercluster at the scale that matters for cosmology, when we step back far enough to take in the entire structure, individual stars disappear from view. They become as invisible as the individual atoms that make up the stars. At the scale of a supercluster, we see not individual stars, but galaxies appearing as bright points of light. And when we zoom out further still, to the scale where we can view the entire cosmic width, even the galaxies become nearly invisible. What we see is the distribution of matter on the largest scales, the vast filaments in voids, the cosmic width that extends throughout the observable universe. The Hercules supercluster, or whatever we choose to call this vast structure, appears in surveys as a large concentration of galaxies, denser than the average cosmic background, but not overwhelmingly so. It extends across a region of space measuring roughly 2 billion light-years or more from one end to the other, though defining the precise boundaries of such a structure is somewhat arbitrary, as it gradually transitions into the surrounding regions of space rather than having a sharp edge. Within this vast volume of space, the density of galaxies is somewhat higher than the cosmic average, forming what appears to be a kind of wall or filament within the larger cosmic web. When cosmologists and astronomers study such structures, they employ a variety of techniques and approaches. One of the most important is the analysis of the peculiar velocities of the galaxies within the structure. In addition to the systematic expansion velocity that all galaxies have due to the expansion of the universe itself, individual galaxies also have their own local motions, their own velocities relative to their neighbors. These peculiar velocities are typically much smaller than the expansion velocity, but they are not negligible. The pattern of peculiar velocities within a structure can reveal information about the gravitational field at work within that structure, and in particular, about where the concentrations of matter are located. When astronomers measure the peculiar velocities of galaxies within and around structures, like the Hercules supercluster, they find that the galaxies show systematic infall motions toward the denser regions. This is exactly what we would expect from gravity. Galaxies in the less dense regions are being pulled toward the denser regions by gravitational attraction. This confirms that the structures we observe are indeed bound together by gravity, that they represent genuine accumulations of matter rather than mere illusions created by our viewing angle or by some other observational bias. But what is striking about the peculiar velocity patterns is how extensive the regions of inflow are. Galaxies that are located hundreds of millions of light years away from the main concentration of matter in these structures still show evidence of being pulled toward them. The gravitational influence of these massive structures extends far into the surrounding space. In a sense, each of these vast structures is a kind of cosmic attractor, a region of space that is pulling matter toward itself from enormous distances. The universe, on these large scales, is engaged in a kind of cosmic dance, with matter flowing along the filaments from the voids toward the clusters, and with gravity orchestrating the entire performance. Now, let us consider what this all means for our understanding of the universe, and for our place within it. We live in a galaxy, the Milky Way, that is located within a group of galaxies called the local group. This group contains perhaps 80 galaxies, including the Milky Way and the Andromeda Galaxy, which at about 1 trillion stars is somewhat more massive than our own galaxy. The local group, in turn, is located within a larger supercluster, sometimes called the Virgo supercluster, named for the Virgo cluster, the largest and most massive galaxy cluster within it. And the Virgo supercluster, itself a structure spanning hundreds of millions of light years, appears to be embedded within an even larger structure, perhaps part of what is sometimes called the Laniakea supercluster, a vast collection of superclusters spanning over 1 billion light years. This hierarchy of structures, from our local group to the largest superclusters, is not just a product of the gravitational clumping of matter. It also carries within it a kind of cosmic history, a record of the processes that have been at work since the beginning of time. Each structure represents the accumulated effect of gravity pulling on the sea fluctuations that existed in the early universe. The largest structures represent the largest scale fluctuations, the broadest patterns in the density variations that were imprinted on the universe when it was less than a second old. In this light, the Hercules supercluster and the other vast structures that have been discovered in recent decades represent something quite profound. They are cosmic monuments to the growth of structure under gravity, records of nearly 14 billion years of cosmic evolution. They are also, in a very real sense, mysteries. They are structures that seem to exceed what our current models predict should be possible. And in their existence, they call out to us to reconsider, to revise, to expand our understanding of how the universe works. There is something deeply humbling about contemplating these structures. We sit here on this small planet, orbiting an ordinary star, within an ordinary galaxy, within a supercluster that is itself just one of many in the cosmos, and we have managed, through observation and mathematics, to detect and measure structures on scales that dwarf anything we can directly perceive. We have mapped the universe across billions of light years, and we have found that it is far more complex and far more strange than we would have guessed. And yet, there remains an almost poetic symmetry in our situation. We are made of matter that was forged in the cores of stars, that was scattered across space by supernova explosions, and that eventually accumulated into the earth and into our cells. The atoms in our bodies were created in the hearts of dying stars, and they have been recycled through countless cosmic processes over the course of billions of years. In a very real sense, we are made of stardust, of the debris of ancient stars that exploded long before our sun was born. And the structure of the universe that we observe, the vast filaments and clusters and walls of galaxies, are themselves products of the same gravitational processes that operate on all scales, from the clustering of atoms within molecules, to the gathering of matter into stars, to the assemblage of stars into galaxies, to the grouping of galaxies into superclusters. This realization that we are connected through matter and through the laws of physics to the entire cosmos is one of the great insights of modern science. We are not separate from the universe, observing it from some external vantage point. We are part of it. We are made of it. And in studying the universe, we are studying ourselves. We are investigating the material circumstances of our own existence. But let us return to the specific question that has motivated much of this discussion, the question of how structures this large could have possibly formed in the time available. There are indeed some theoretical possibilities that deserve consideration, some ways of understanding the physics that might allow for the existence of these vast structures without requiring a fundamental overhaul of our cosmological models. One possibility involves the nature of the initial density fluctuations themselves. We have assumed that these fluctuations follow a particular distribution, described by what is called a power law or a power spectrum. The precise shape of this power spectrum is one of the things that is most directly measured by observations of the cosmic microwave background. But while the general features of the power spectrum are fairly well constrained by observations, there remains some uncertainty about the details, particularly on very large scales. If the initial fluctuations were somewhat more pronounced on large scales than we currently believe, then the structures that form from them might be able to grow faster and reach larger sizes than our current models predict. This is an area of active research, with new observations and improved measurements continually refining our understanding of the power spectrum of cosmic fluctuations. Another possibility involves the behavior of dark matter in more detail. We know that dark matter comprises the majority of the matter in the universe, and that it plays a crucial role in structure formation. But our understanding of dark matter remains incomplete. In particular, we do not know whether dark matter particles interact with each other in ways beyond simple gravity. Some theoretical models propose that dark matter might be self-interacting, meaning that dark matter particles could collide with each other and exchange momentum. If dark matter is self-interacting, then this could affect the way that dark matter structures form and evolve, potentially allowing for more efficient structure growth than our current models predict. Yet another avenue of exploration involves the possibility that the structures we observe, while certainly real and certainly massive, might not be quite as large as they initially appeared to be. This is not a retreat from observation, but rather a more careful interpretation of the data. When we measure the size of a structure, we rely on measurements of galaxy positions and distances. These measurements, while quite accurate by astronomical standards, do have uncertainties. Moreover, the definition of what constitutes a structure is somewhat subjective. There is no sharp boundary between a supercluster and the surrounding universe. Instead, there is a gradual transition, with density increasing as one moves toward the center and decreasing as one moves away. Depending on where exactly we choose to define the boundary of a structure, we will get different estimates of its size. In recent years, some researchers have questioned whether the Sloan Great Wall and similar structures really are single unified entities, or whether they might be better understood as loose collections of smaller structures that happen to project onto a single wall-like appearance when viewed from our vantage point. This would not necessarily mean that the structures do not exist or that they are not extraordinarily large. It would just mean that they might be somewhat smaller or somewhat less tightly bound than an initial reading of the data might suggest. This is the kind of careful re-examination and refinement of our understanding that science continually engages in, as new data becomes available and as our techniques of analysis improve. But even accounting for these various theoretical possibilities and refinements, there remains a tension between what our models predict and what we observe. The structures we see are somewhat larger than we would have expected. This tension has led some cosmologists to consider more radical revisions to our understanding of cosmic structure formation. Some have proposed modifications to the laws of gravity itself on the largest scales, exploring whether Einstein's general relativity might need to be supplemented or revised to account for observations on these extreme scales. Others have proposed that dark energy might not be quite as simple as we have assumed, that it might vary over space or time in ways that could affect structure formation. These more radical proposals remain speculative at this point, and they are not widely accepted by the cosmological community. But they exemplify an important aspect of how science progresses. When observations do not match predictions, we are forced to consider new possibilities, new directions of investigation. The standards of evidence for accepting such radical revisions are very high, and rightly so. But the possibility remains open, and as observations continue to improve, and as our understanding deepens, we may find that some revision of our current understanding is indeed necessary. Now, let us step back from the technical details for a moment and consider the larger implications of what we have been discussing. The existence of these vast structures, whether or not they present a fundamental challenge to our current cosmological models, tells us something important about the nature of the universe and about our place within it. It tells us that the universe is not a featureless fog of evenly distributed matter, but rather a complex network of structures at many different scales. It tells us that gravity, that most fundamental and most long range of the forces in nature, is responsible for organizing matter on scales ranging from planets and stars to galaxies to superclusters to the largest structures that exist. It also tells us something about the character of scientific inquiry itself. Science is not a process of discovering final, unchangeable truths about the nature of reality. Rather, it is an ongoing dialogue between observation and theory, between what we can measure and what we can understand. When observation and theory diverge, that divergence is not a failure of science. It is an opportunity, an invitation to refine and improve our understanding. The history of science is full of examples of such productive divergences. The observations that did not match the predictions of Newtonian physics led to the development of Einstein's theories of relativity. The observations that did not match the predictions of classical physics in the late 19th century led to the development of quantum mechanics. In each case, the apparent contradiction between observation and theory was resolved not by abandoning one or the other, but by developing new and more comprehensive frameworks that encompass both. It is entirely possible that the existence of these vast cosmic structures will play a similar role in the further development of cosmology. Perhaps they will lead to modifications in our understanding of dark matter or dark energy. Perhaps they will lead to refinements in our understanding of how the initial conditions of the universe were established. Or perhaps they will reveal some entirely new aspect of physics that we have not yet recognized. In any case, they serve as a reminder that the universe remains, in many ways, mysterious, and that there is much yet to be learned. As we contemplate these structures, we might also consider what they tell us about the deep past. These vast structures took billions of years to form, growing slowly through the patient accumulation of matter drawn together by gravity. They represent the history of the universe written in the distribution of matter across space. In studying them, we are in a sense reading the cosmic history book, deciphering the record of how the universe has evolved from the smooth, nearly featureless state of the early universe to the complex, structured universe we observe today. The very earliest moments of the universe, according to our current understanding, were dominated by quantum effects, by processes that occurred at scales so small and at temperatures so high that our current physical theories break down and become unreliable. In these first fractions of a second, the universe underwent what is called inflation, a period of extraordinarily rapid expansion during which it expanded by many orders of magnitude in an incredibly brief time. During this inflationary period, quantum fluctuations in the density of matter and energy were stretched to macroscopic scales, becoming the seed fluctuations from which all future structures would grow. After inflation ended, the universe continued to expand and cool, but now at a much slower rate. Particles formed from the energy released during the Big Bang. Protons and neutrons assembled into light atomic nuclei, primarily hydrogen and helium. These nuclear building blocks would later assemble into the first stars and galaxies. But before that could happen, a long dark age had to pass, a period of several 100 million years during which the universe was essentially empty of stars and galaxies, containing only a diffuse gas of hydrogen and helium, permeated by dark matter, and seeded with the tiny density fluctuations that would eventually grow into structures. During this dark age, gravity was at work, pulling together the dark matter and the ordinary matter in regions of slightly higher density. These accumulations grew slowly at first, but as they grew larger, their gravitational effects became stronger, and they began to grow more rapidly, a process called gravitational instability or runaway growth. After several 100 million years, the densest regions had grown enough that gas within them could collapse and heat up enough to initiate nuclear fusion, and the first stars were born. These first stars were very different from the stars we see today. They were composed entirely of hydrogen and helium, with no heavier elements, because the universe had not yet had time to produce elements heavier than helium through nuclear fusion in stars. The first stars were also massive and short-lived, burning brightly for only a few million years before exploding in supernova explosions. In the cores of these massive stars, nuclear fusion had created heavier elements, iron and nickel and silicon and many others, elements that had not existed since the Big Bang. When these first stars exploded, they scattered this newly created matter across space, seeing the interstellar medium with the chemical elements that would eventually be incorporated into new generations of stars, and eventually into planets, and eventually into life. This process has continued throughout the history of the universe. Stars are born, they create heavy elements in their cores, they eventually die and distribute their enriched material back into space. This material becomes part of new stars and planets. The universe slowly enriches itself with heavier and heavier elements. The Sun and the planets that orbit it, including the Earth, were formed from material that had been processed through many generations of stars. The carbon in our bodies, the oxygen that we breathe, the iron in our blood, all of these elements were created in the cores of stars that lived and died billions of years ago. And fraying through all of this cosmic history has been the slow, patient work of gravity, gathering matter into denser and denser concentrations, building structures at every scale from the tiniest black holes to the largest superclusters. The vast structures that we observe today, the walls and filaments of galaxies spanning billions of light years, are the products of this long-term gravitational evolution. They embody within their structure the entire history of the universe, from the first infinitesimal fractions of a second after the Big Bang, to the inflationary epoch, to the dark age when the first stars had not yet formed, to the epochs of star formation and chemical enrichment, to the present day. In this light, the question of whether these structures are larger than our models predict becomes something more than a technical puzzle for cosmologists to solve. It becomes a question about the fundamental history of the universe itself. It raises the possibility that some aspect of this history, some process that has been occurring over the course of billions of years, might not be fully captured in our current models. It invites us to look deeper, to observe more carefully, to theorize more boldly. It suggests that we may still have much to learn about how the universe works, even on the most fundamental levels. Let us now consider in more detail what we know about the structure of the Hercules supercluster itself, for this particular structure provides an especially instructive example of the types of mysteries we have been discussing. The Hercules supercluster, as its name suggests, is located in the direction of the constellation Hercules as viewed from Earth. It lies at a distance of approximately 700 million light-years away, which places it well within the observable universe, and within range of our most powerful telescopes. Because it is relatively nearby, cosmologically speaking, it has been the subject of extensive observation and detailed study. The supercluster consists of a number of major galaxy clusters, connected together into a larger structure. These clusters include the Hercules cluster itself, one of the most prominent features, along with the Abell 2151 cluster and several others. Within these clusters, individual galaxies range from small dwarf galaxies containing only a few billion stars, to giant elliptical galaxies containing over 1 trillion stars. The total count of galaxies within the Hercules supercluster is in the tens of thousands, and the total mass, including dark matter, is inconceivably large. When astronomers map out the three-dimensional distribution of galaxies within and around the Hercules supercluster, they find that the structure is not a simple, symmetric arrangement. It is not a perfect sphere or a regular polyhedron. Rather, it is an irregular, elongated structure, somewhat flattened and twisted, reflecting the complex dynamics of the gravitational forces at work. In some regions, the density of galaxies rises quite sharply, creating knots of concentration. In others, there are filaments connecting these knots, along which galaxies are preferentially distributed. And in still others, there are voids where galaxies are sparsely distributed or nearly absent. This complex structure tells a story about the forces that have shaped the supercluster over billions of years. The filaments and knots represent places where the gravitational inflow of matter has been efficient, where matter from surrounding regions has been drawn together into denser accumulations. The voids represent places where matter has been depleted, drawn away toward the denser regions. This process, called cosmic structure formation, has been ongoing ever since the dark matter began to accumulate in the early universe. In a sense, we are watching the present-day result of billions of years of gravitational reorganization of matter. One of the most intriguing aspects of the Hercules supercluster is the fact that it appears to be in a state of relative dynamical coherence. What this means is that the galaxies and clusters within the supercluster are moving in a coordinated way, as if bound together by a common gravitational influence. The peculiar velocities that we mentioned earlier, the local motions of galaxies relative to the cosmic expansion, show patterns that are consistent with the various components of the supercluster being pulled together by their mutual gravitational attraction. This indicates that despite the vast distances involved, the gravitational connection between the different parts of the supercluster remains significant. This is a remarkable fact when one considers the distances involved. The gravitational force falls off as the inverse square distance, meaning that the force becomes very weak at very large distances. Yet the gravitational influence of the dense central regions of the supercluster is still strong enough to produce detectable effects on galaxies located hundreds of millions of light-years away. This speaks to the enormity of the mass involved, and it provides us with a way of measuring the total mass of the supercluster by analyzing the patterns of galaxy motions within and around it. When astronomers perform these measurements, they find that the total mass of the Hercules supercluster is roughly 1,000,000 billion times the mass of our own Sun, a number so large that it defies comprehension. If we were to express this in scientific notation, it would be something like 10 to the 15 solar masses. To put this in perspective, The entire observable universe, with all its galaxies and stars and planets and asteroids, contains a total mass that is many trillions of times this number. But still, the fact that a single supercluster can contain such an enormous amount of mass is testimony to the vast scales at which the universe operates. Now, we might ask, how confident are we in our measurements of these large-scale structures? Are we certain that we are observing them correctly? These are excellent questions, because good science demands that we be critical of our methods and our conclusions. The observations of large-scale structures are based on several different techniques, each with its own particular strengths and weaknesses. By employing multiple techniques and comparing the results, astronomers have been able to cross-check their measurements and gain confidence that the structures they observe are real. One of the primary observational techniques involves measuring redshifts, as we discussed earlier. By measuring the wavelength shift of light from distant galaxies, we can determine their distances from us with reasonable accuracy. This technique is quite robust, and it has been employed for many decades with consistent results. But it is not infallible. There are systematic uncertainties in the measurement of redshifts, and there are also uncertainties in the conversion from redshift to distance, which depend on our assumptions about the composition and expansion rate of the universe. Another observational technique involves measuring the brightness of galaxies and using that to estimate their distances. Galaxies of a similar type tend to have similar intrinsic brightness, so by measuring their apparent brightness as seen from Earth and comparing that to their presumed intrinsic brightness, we can estimate their distance. This technique, called the distance modulus method, is also widely used, but it also has sources of uncertainty. The intrinsic brightness of a galaxy is not always easy to determine, and dust in the galaxy itself or in the intergalactic medium can dim the light we receive, leading to overestimates of distance. A third observational technique involves measuring the peculiar velocities of galaxies using the Doppler shift of light. If a galaxy is moving toward us or away from us, the light we receive from it will be shifted to shorter or longer wavelengths respectively. By measuring the Doppler shift and accounting for the motion that would be expected from the universal expansion alone, we can determine the galaxy's peculiar velocity. If we have measured enough galaxies, we can build up a map of the peculiar velocity field in a region of space, and from this we can infer the distribution of matter that is giving rise to this peculiar velocity pattern. These various observational techniques, when applied to the Hercules supercluster and similar structures, all point to the same conclusion. These vast structures do indeed exist, and they are nearly as large as the redshift measurements suggest. While there are certainly uncertainties in the precise sizes and distances involved, the reality of these structures is not in doubt. Multiple independent lines of evidence all confirm their existence. But if the structures are real, and if they are indeed nearly as large as they appear, then we must return to the theoretical question: how can such large structures have formed in the time available? This question remains partially unresolved, and it is an active area of research in theoretical cosmology. There are several different avenues of investigation being pursued, and it is quite possible that the resolution will involve some combination of these different approaches. One avenue involves more detailed and more careful modeling of structure formation. The simplest models treat structure formation as a linear process in the early universe, meaning that the growth of density fluctuations can be calculated using linear perturbation theory, a mathematical technique that works well when the fluctuations are small. As the fluctuations grow larger, however, the linear approximation breaks down, and we must employ more complex nonlinear models. These nonlinear models are computationally intensive, requiring massive simulations performed on supercomputers, but they can potentially reveal ways that structures might grow faster or more efficiently than simple linear models predict. Another avenue involves reconsidering the initial conditions of the universe. The inflationary theory of cosmology, which is widely accepted and which has proven quite successful at explaining many features of the universe, does not uniquely determine what the initial density fluctuations should be. Different versions of inflation can produce different spectra of fluctuations, and while most of these are consistent with observations of the cosmic microwave background, some versions can produce somewhat more prominent fluctuations on large scales than others. If the initial fluctuations were somewhat larger than we currently believe, then the structures they seed would grow faster and reach larger sizes more readily. A third avenue involves exploring whether there might be non-gravitational processes that contribute to structure formation. In addition to gravity, the physics of the early universe involves electromagnetic forces, the strong and weak nuclear forces, and other interactions. While gravity dominates the large-scale structure formation, it is conceivable that other forces might play a subtle role that we have not yet fully appreciated. For instance, there might be processes related to the interaction of dark matter with other particles, or fields that could influence structure growth in ways we have not yet considered. Yet another avenue involves the possibility that the very existence of these large structures might tell us something important about the physics of the early universe. If structures larger than our models predict have indeed formed, perhaps this is telling us that the early universe was not quite as smooth and uniform as we have assumed. Perhaps the seed fluctuations were somewhat more structured, somewhat more organized than a simple Gaussian random field would produce. This possibility has led some theorists to explore alternatives to inflation or modifications of inflation that might produce a different spectrum of initial fluctuations. As we contemplate these various possibilities, we should remember that science is a process of gradual refinement and improvement. It is not necessary that any one of these approaches will provide the complete answer. It is quite possible that the resolution of this puzzle will involve a combination of factors: slightly larger initial fluctuations than we currently believe, somewhat more efficient structure growth than our models currently predict, and perhaps some currently unexpected physical process that we have not yet recognized. The truth, as is often the case in science, may be more subtle and more complex than any single hypothesis can capture. But in addition to the technical puzzles involved, there is something philosophically profound about contemplating these vast structures. They represent, in a very real sense, the universe examining itself. We are made of matter that was forged in stars. The atoms in our brains were created in supernova explosions. The calcium in our bones, the iron in our blood, the oxygen that sustains our life, all of these were made by processes occurring inside stars or in nuclear reactions in the early universe. We are not separate from these vast cosmic structures. We are part of them. We have arisen from the matter that makes up these structures, and we are capable of understanding them, of measuring them, of theorizing about them, of writing down the mathematical laws that govern their behavior. This is an extraordinary fact, one that deserves to be contemplated with something approaching awe. The universe has, through billions of years of evolution, produced conscious beings capable of understanding the universe itself. We are a way for the cosmos to know itself, to contemplate its own nature, to marvel at its own grandeur. And the vast structures that we have been discussing, the superclusters stretching across billions of light years, the filaments and voids composing the cosmic web, these are not merely objects of observation and measurement. They are part of the context of our existence, the cosmic environment in which we emerged. When we observe the Hercules supercluster or the Sloan Great Wall, we are observing manifestations of physical laws that have been operating continuously since the moment of the Big Bang, perhaps since before the Big Bang, if we accept certain speculative cosmological models. We are observing the long-term consequences of gravity acting on matter across billions of years. We are witnessing, in a very real sense, the unfolding of a vast cosmic drama that has been developing since the very beginning of time. And in observing these structures, in measuring them, in struggling to understand them within the frameworks provided by our theories, we are engaging in one of the most characteristically human activities. We are asking questions about the nature of reality. We are not accepting the apparent mysteries of existence as permanently closed, but rather we are approaching them with curiosity and with the tools of reason. This is the essence of the scientific endeavor, and it represents one of humanity's most noble aspirations. The existence of these vast structures that seem to exceed the predictions of our models is not a failure or a defeat of science. Rather, it is an invitation, an opportunity to think more deeply, to observe more carefully, to construct new theories, and to test them against the evidence provided by nature. The cosmos has presented us with a puzzle, and in solving that puzzle, we will deepen our understanding of how the universe works. We will refine our knowledge, correct our errors, and approach ever closer to truth, even if that truth remains infinitely more vast and more complex than any finite mind can fully comprehend. The discovery of the Sloan Great Wall and other vast cosmic structures in the early years of the 21st century represents a turning point in our understanding of the universe. For many decades prior to this discovery, cosmologists had believed that they understood the basic principles of how the universe was structured and how that structure came to be. The theory of cosmic inflation, developed in the 1980s, had provided a compelling explanation for the origin of the density fluctuations from which all structure grew. The theory of structure formation, based on the physics of gravity and dark matter, had explained how those seed fluctuations grew into galaxies, clusters, and superclusters. And the observations seemed to confirm the predictions of these theories, at least in broad outline. But the discovery of structures larger than theory predicted represented a kind of wake-up call, a reminder that the universe is still capable of surprising us, that our understanding, while sophisticated, remains incomplete. It forced cosmologists to reconsider their assumptions, to examine their models more critically, to think about whether modifications or fundamental revisions might be necessary. In this sense, the existence of the Sloan Great Wall and similar structures serves an important function. It keeps us honest. It prevents us from becoming too confident in our understanding, too comfortable with the models we have constructed. This is, in fact, the proper attitude for science to take toward its own knowledge and understanding. Science is not a body of finished truths, set in stone, unchangeable and eternal. Rather, it is a dynamic process, an ongoing dialogue between observation and theory, a continuous refinement and improvement of our understanding in light of new evidence. The greatest scientists understand this. They know that their theories, however elegant and however well tested, may one day be superseded by better theories that account for more observations with greater precision. The history of science is full of examples of theories that were once considered nearly certain to be true, only to be later superseded or substantially revised. Newtonian mechanics, which gave an excellent description of the motion of macroscopic objects, and which seemed to provide a complete understanding of gravity, was later found to be only an approximation, valid at low speeds and weak gravitational fields, but requiring relativistic corrections at higher speeds and in stronger fields. Classical electromagnetism, which seemed to be a complete destruction of electromagnetic phenomena, was found to be incompatible with the laws of mechanics, leading to the development of quantum mechanics. The steady-state theory of the universe, which proposed that the universe had no beginning and had always existed in a roughly constant state, was later disproven by observations of the cosmic microwave background and replaced by the Big Bang theory. In each of these cases, the apparent crisis, the discovery that observation did not match theory, led not to the collapse of science, but to its advancement. New frameworks were developed that resolved the discrepancies, that unified previously separate theories, that explained more phenomena with greater precision. And in each case, the new frameworks revealed aspects of reality that the previous theories had not been able to perceive or understand. This is the way that science progresses, to a series of revolutions in understanding, each building on what came before, but also transcending it, revealing deeper levels of comprehension. It is entirely possible, perhaps even likely, that the same process will occur with respect to the puzzle of the large cosmic structures. The resolution of this puzzle will require us to think in new ways, to revise some aspect of our understanding, to move to a deeper level of comprehension. The process will not be instantaneous. It will take years or decades of research, of careful observations, of theoretical work, of bold hypotheses and careful tests of those hypotheses. But ultimately, the puzzle will be solved, and in the process of solving it, our understanding of the universe will be deepened. And perhaps the most important insight to be drawn from the existence of structures larger than theory predicts is not the specific resolution of this particular puzzle, but rather the more general recognition that the universe continues to surprise us, continues to reveal depths that we had not yet fathomed. For all of our knowledge, for all of the progress that science has made in understanding the cosmos, there remains vastness, complexity, mystery. The universe is not a closed book, with all the pages read and all the secrets revealed. It is an open book, an infinite book, and we are only at the beginning of the process of learning to read it. In contemplating the cosmos, in studying its structures and trying to understand the laws that govern them, we are engaging in an activity that connects us to the deepest aspects of human experience. We are seeking meaning in the universe. We are trying to understand our place in the grand scheme of things. We are pursuing truth and wisdom. These are ancient human aspirations, activities that have occupied humans since the dawn of consciousness. And in the modern era, with our telescopes and computers and mathematical tools, we are carrying forward this ancient quest in new ways, bringing new resources to bear on the fundamental questions about the nature of existence. The fact that we can observe the vast cosmic structures, that we can measure them, that we can develop theories to explain them, is itself a profound statement about the nature of consciousness and the nature of the universe. It says something remarkable about the fact that the universe has produced within itself conscious beings capable of understanding its own structure and evolution. We are not separate observers of the cosmos, viewing it from the outside. We are part of the cosmos. The atoms that make up our bodies were forged in stars. The chemistry of our brains is the chemistry of the universe. In studying the cosmos, we are studying ourselves, we are investigating the material basis of our own existence, we are contemplating the context out of which we have emerged. With these new instruments, astronomers will be able to make more precise measurements of the universe's structure. They will be able to identify and characterize large-scale structures with greater accuracy. They will be able to measure the properties of galaxies, clusters, and filaments more precisely than ever before. And they will be able to test theoretical predictions against observations with a level of detail that has not previously been possible. This work will undoubtedly lead to a better understanding of how cosmic structures form and evolve, and it will very likely shed light on the puzzle of how structures as large as the Hercules supercluster and the Sloan Great Wall could have possibly formed in the time available. Moreover, the field of computational astrophysics is advancing rapidly. Supercomputers are becoming more powerful, and simulation techniques are becoming more sophisticated. This makes it possible to perform increasingly detailed simulations of the universe, starting from the initial conditions implied by observations of the cosmic microwave background and evolving forward to the present day, following the growth of structures under gravity. These simulations can help us understand the physical processes at work in structure formation. They can help us test different theoretical models against observations. And they can help us identify new possibilities that we might not have considered without the computational tools to explore them. The combination of improved observations and improved simulations will undoubtedly advance our understanding substantially. Very likely, the puzzle of the large structures will be resolved within the coming decades, as our measurements become more precise and as our theories become more sophisticated. Whether the resolution will involve a revision of our understanding of dark matter or dark energy, a modification of the theory of cosmic inflation, a reconsideration of the initial conditions of the universe, or some completely new physical insight that we have not yet anticipated, we cannot yet know. But we can be confident that in resolving this puzzle, we will deepen our understanding of the cosmos and of the fundamental laws of physics that govern its behavior. And as we work toward these answers, we should remember that the ultimate goal is not merely to accumulate more facts about the universe or to refine our measurements and calculations. The ultimate goal is understanding, is wisdom, is the achievement of genuine insight into the nature of reality. The vast structures we have discussed, the Hercules supercluster, the Sloan Great Wall, and all the other cosmic structures that are yet to be discovered and characterized, are more than just objects of scientific curiosity. They are expressions of the fundamental laws and principles that govern the universe. In understanding them, we are understanding the universe itself. We are understanding the context in which we exist, the material basis of our own existence, the cosmic environment that gave birth to our galaxy, our star, and our planet. In this sense, the study of cosmic structures is deeply connected to some of the most fundamental questions that humans have always asked. Where do we come from? How did we get here? What is the nature of the universe? Are we alone? These are ancient questions, questions that have occupied human thinkers for thousands of years. The answers that science is beginning to provide to these questions are not the same as the answers offered by myth or religion, but they are no less profound. They reveal a universe of extraordinary complexity and beauty, a cosmos in which the laws of physics operate with remarkable consistency and precision across scales ranging from the subatomic to the cosmic, a universe in which consciousness has somehow emerged and become capable of understanding itself. The journey of discovery is far from complete. We have made remarkable progress in our understanding of the cosmos, but there is much more to learn. The mysteries that remain, the nature of dark matter and dark energy, the initial conditions of the Big Bang, the origin of the universe itself, the possibility of other universes. These are profound questions that may take decades or centuries to resolve fully. But in the process of working toward their resolution, in the process of making observations, developing theories, testing those theories against evidence, we are engaged in one of humanity's most noble endeavors. We are pursuing truth. We are seeking to understand the world in which we live. And we are expanding the boundaries of human knowledge and human consciousness. So let us appreciate the vast cosmic structures, these monuments to the power of gravity and the patience of time. Let us marvel at the fact that we can observe them, that we can measure them, that we can theorize about them, and that we are slowly but surely coming to understand them. Let us recognize that in contemplating these structures, we are contemplating our own cosmic context, our own place in the universe, the material circumstances that gave rise to us. And let us approach the mysteries that remain with humility, with curiosity, and with the confidence that through careful observation, mathematical analysis, and bold theorizing, we can continue to deepen our understanding of the cosmos and our place within it. The discovery of vast cosmic structures that seem to exceed the predictions of our theories is not an ending to the scientific investigation of the cosmos. Rather, it is a beginning, an opening of new avenues of inquiry, a challenge to think in new ways. It is in precisely these moments, when observation and theory diverge, when nature presents us with phenomena that do not fit neatly into our existing categories, that science has the opportunity to advance. These are the moments of genuine discovery, when we are forced to revise our understanding, to venture into new territories of thought, to approach the cosmos with fresh eyes and renewed humility. As we contemplate the vast structures that populate the cosmos, as we struggle to understand their nature and their origin, we are engaged in something far more profound than the mere accumulation of facts about the physical world. We are engaged in a fundamental human endeavor, an attempt to understand ourselves and our place in the universe. We are seeking meaning in the cosmos, trying to grasp what it all means, how it all fits together. In doing so, we are participating in one of humanity's greatest achievements, the creation of a body of knowledge about the natural world, a body of knowledge that is always growing, always being refined, always becoming more complete and more accurate. The Hercules supercluster, the Sloan Great Wall, and all the other vast structures we have discussed are real. They exist. They have existed for billions of years, gradually accumulating matter under the pull of gravity, slowly growing from small seed fluctuations to the enormous structures we observe today. And they will continue to exist for billions of years into the future, slowly evolving as the universe expands and cools, and gradually transitions to a state where dark energy completely dominates, and the growth of structures essentially ceases. But perhaps the most remarkable thing about these structures is not their size, or their mass, or even their theoretical interest to cosmologists and physicists. Perhaps the most remarkable thing is the fact that we know about them at all. We know about them because there are beings, here on a small planet orbiting an ordinary star, who are capable of reaching out with their minds, who have built instruments to extend the reach of their senses, who have developed the mathematical and conceptual frameworks necessary to understand these vast structures. We know about them because of the combined efforts of countless astronomers, physicists, mathematicians, and engineers, working across generations, building on each other's insights and discoveries, slowly accumulating a vast body of knowledge about the universe. And in knowing about these vast cosmic structures, in understanding them to the extent that we do, we are participating in something profound. We are extending the reach of consciousness into the universe. We are causing the universe to become aware of itself. We are transforming the mindless matter and energy of the cosmos into conscious understanding. This is a transformation that would have seemed impossible to the ancients, who could only look up at the stars with wonder and bewilderment. But through the power of reason, through the patient accumulation of knowledge, through the development of increasingly sophisticated tools and techniques, we have managed to achieve something remarkable. The vast structures that stretch across billions of light years are now known to us. They are no longer hidden in darkness, accessible only to the most sophisticated instruments. They exist in our minds, in our theories, in our mathematical models. We have mapped them, measured them, and analyzed their properties. We have striven to understand how they came to be, what forces shaped them, what their presence tells us about the fundamental nature of reality. And yet, much remains unknown. We do not fully understand how these structures became as large as they are. We do not fully understand the nature of dark matter and dark energy. We do not fully understand the initial conditions of the universe or the processes that occurred in its first infinitesimal fractions of a second. The cosmos, for all the progress we have made in understanding it, retains its essential mystery. There are questions for future generations to answer, discoveries for future astronomers and physicists to make. This is as it should be. A universe that we had completely understood would be a disappointing thing, a puzzle with all its pieces laid out before us, its solution obvious. But the universe continues to surprise us, to present us with phenomena that do not fit neatly into our existing frameworks, to challenge us to think in new ways. And in those challenges lies hope, lies the promise of future discovery, lies the possibility that we will continue to deepen our understanding and extend the reach of human knowledge. As we look to the future, we can anticipate that new observations will be made, new telescopes will be built, new data will be collected. The universe will continue to reveal its secrets slowly, patiently, to those who know how to look and how to listen. And as our knowledge grows, as our understanding deepens, we will find ourselves in a strange and wonderful position. We will be citizens of a cosmos that is far vaster and far more complex than our ancestors could have imagined. And yet, we will possess the conceptual tools and the accumulated knowledge necessary to understand it. We will be made of stardust, contemplating the stars from which we came. We will be conscious manifestations of the universe, capable of understanding itself. And perhaps in the distant future, long after we are gone, long after our civilization is passed into history, there will be others who continue this work of understanding, who ask their own questions about the nature of the cosmos, who make discoveries that we cannot yet imagine. They will stand on the shoulders of giants, building on the foundation of knowledge that we have constructed. They will have access to instruments and techniques that we could only dream of, and they will face mysteries that are even deeper than those that confront us today. For such is the nature of knowledge and understanding. They are not destinations to be reached, but journeys to be undertaken. Each answer we discover leads to new questions. Each mystery we solve reveals deeper mysteries beyond. The universe is infinite, and our understanding of it, while growing ever more sophisticated and more complete, can never be complete. There will always be more to learn, always be new vistas to explore, always be deeper levels of understanding to achieve. And so we are brought back to where we began, to those vast cosmic structures that should not exist, that push the boundaries of our understanding, that challenge us to think in new ways. These structures are real. They exist in the cosmos, indifferent to our theories and our models. And in attempting to understand them, we are engaging in one of the most human of endeavors, the attempt to comprehend the world in which we live. We are seeking understanding, seeking meaning, seeking truth. And in that seeking, we are participating in one of humanity's greatest achievements, the advancement of knowledge and the deepening of our understanding of the natural world. Let us consider for a moment the profound implications of what we have been discussing, implications that extend far beyond the boundaries of theoretical cosmology and into the deepest questions of metaphysics and philosophy. The universe we observe is not a simple place. It is layered with complexity upon complexity, with structures nested within structures, with scales extending from the subatomic realm to the incomprehensibly vast distances between superclusters. And at every scale, we find that the same fundamental principles are at work, the same laws of physics operating, the same patterns emerging again and again in different contexts and at different magnitudes. The physicist and philosopher David Hume once asked a profound question: why should we expect the universe to be comprehensible at all? Why should the human mind, which evolved to solve problems on the scale of the African savanna, be capable of understanding the laws that govern the cosmos? It is a remarkable fact that it is, that through mathematics and careful observation, we have been able to discern patterns in nature, to discover laws, to develop theories that allow us to predict and understand phenomena that we can never directly observe. This is not something that should be taken for granted. It is a profound gift, a mystery in its own light. And this mystery becomes even more profound when we consider the particular puzzles that the universe presents to us. The existence of structures larger than theory predicts is not a minor technical issue, something that can be swept aside with a small adjustment to the parameters of our models. Rather, it points to something fundamental, something about the structure of reality itself that we have not yet fully grasped. It suggests that our current understanding, while impressive and sophisticated, is incomplete. It suggests that there are depths yet to be fathomed, mysteries yet to be solved. Throughout the history of science, the most important breakthroughs have come not when everything fit neatly together, not when observation and theory aligned perfectly, but rather when there was a discrepancy, a gap between what was expected and what was observed. The orbit of Mercury, which precessed slightly more than Newton's theory predicted, led to Einstein's general relativity. The observations of certain spectral lines in the light from distant galaxies, which did not behave as expected, led to the discovery of dark matter. The unexpected dimness of distant supernovae, which were not as bright as expected, led to the discovery of dark energy and the realization that the expansion of the universe is accelerating. And now, the existence of structures larger than structure formation theory predicts may lead to the next great breakthrough in our understanding of the cosmos. Perhaps it will lead to a modification of our understanding of how gravity operates on the largest scales. Perhaps it will lead to new insights into the nature of dark matter or dark energy. Perhaps it will lead to a completely new understanding of the initial conditions of the universe, or of the processes that occurred in its first moments. We do not know yet. But we can be confident that in grappling with this puzzle, in striving to understand how these vast structures came to be, we are engaged in work that will ultimately deepen our understanding of the fundamental nature of reality. Let us now expand our contemplation to consider not just the individual structures we have discussed, but the entire cosmic web as it appears to us, with all its complexity and all its beauty. When astronomers map the universe on the largest scales, when they compile the positions and distances of hundreds of thousands or millions of galaxies, a remarkable pattern emerges. The universe is not filled uniformly with galaxies. Rather, the galaxies are concentrated in filaments, in long strands of matter that weave through the cosmic space like the threads of some vast and intricate tapestry. Between these filaments lie voids, regions of near emptiness that can span hundreds of millions of light years across. The entire structure resembles nothing so much as a cosmic web, or perhaps the structure of a neuron, or the branching pattern of a river system. This filamentary structure is not unique to the universe at the largest scales. Similar patterns appear at many different scales throughout nature. The structure of the Internet, with its hubs and nodes connected by links, resembles the cosmic web. The structure of a tree, with its trunk branching into limbs and twigs, resembles it. The structure of blood vessels in a mammalian body, with major arteries branching into smaller and smaller capillaries, resembles it. This recurrence of similar patterns at different scales and in different contexts is called cell similarity, and it is a phenomenon that appears throughout nature with remarkable frequency. The cosmic web, then, is not an arbitrary or random arrangement of galaxies. Rather, it reflects the operation of fundamental physical principles, principles that operate across many different scales and in many different contexts. It is a manifestation, on the grandest scale imaginable, of the process of gravitational instability, the tendency of matter to cluster together under its own gravity, to form denser and denser concentrations as time goes on. This process, which begins with tiny quantum fluctuations in the early universe, ultimately produces the vast structures we see today, stretching across billions of light years. And yet, within this cosmic web, there are regions that stand out as being particularly impressive, particularly massive, particularly interesting from the perspective of cosmology. The superclusters we have discussed, the Hercules supercluster and the Sloan Great Wall and others like them, represent the densest nodes in this cosmic web, the places where the accumulation of matter has been most efficient, where gravity has done its work most thoroughly. These are not typical regions of the universe. They are extremes, outliers on the distribution of structure sizes and scales. And it is precisely because they are extremes, precisely because they represent a kind of maximum achievement of structure formation in the time available, that they present such a puzzle to theory. One of the remarkable facts about the universe is that it appears to be structured in a way that allows for the existence of observers, beings capable of understanding the universe. This is not a trivial fact. It is known in philosophy as the anthropic principle, and it has profound implications for how we think about the universe and about the fundamental laws of physics. The universe could, in principle, have had different laws, different constants, different physical parameters. But if it had, it likely would not have developed stars, and planets, and life, and conscious beings capable of studying the cosmos. The fundamental constants of physics, such as the strength of gravity, the strength of the electromagnetic force, the mass of the electron, all appear to be fine-tuned to permit the existence of complex structures, and ultimately of life. Change any of these constants by even a small percentage, and the universe will be radically different, likely without stars or planets or life. This is sometimes taken as evidence for a multiverse, for the existence of many universes with different physical laws, in which case it is only in those universes whose constants allow for observers that observers could exist to measure those constants. Or it is taken as evidence for some kind of cosmic design or purpose. Or it is simply accepted as a profound mystery, a remarkable coincidence that we may never fully explain. But there is another aspect of the anthropic principle that is perhaps even more profound. Not only are the fundamental constants fine-tuned to permit the existence of observers, but the universe appears to have the structure necessary to produce such observers within a reasonable timescale. If the universe had been slightly less lumpy, if the seed fluctuations in the early universe had been slightly smaller, then structure formation would have proceeded more slowly, and stars and galaxies and life might never have had time to develop before the universe had expanded and cooled to the point where structure formation became impossible. Conversely, if the universe had been much lumpier, if the initial fluctuations had been much larger, then structure formation might have proceeded so violently that the universe would have collapsed back on itself or become dominated by black holes before life had a chance to emerge. The universe, in other words, is structured in a way that is just right for observers to exist. This is a remarkable fact, one that deserves to be contemplated with genuine awe and wonder. It is not necessary to invoke any god or designer to be impressed by this fact. It is enough to recognize that the universe, in its fundamental structure, in its laws, in its initial conditions, possesses a kind of elegant balance, a balance that has permitted the development of complexity, intelligence, and consciousness. And the vast cosmic structures we have been discussing are part of this balance. They represent the long-term consequences of the fundamental laws of physics operating over billions of years. They embody within their structure the entire history of the universe, from the moment of the Big Bang to the present day. They are monuments to the power of gravity, to the way that matter and energy naturally organize themselves into structures of increasing complexity. And they are also mysteries, structures that challenge our understanding and that call us to look deeper, to think more carefully, to approach the cosmos with renewed humility and renewed wonder. As we contemplate these vast structures, we might also consider what they tell us about the future of the universe. The universe, as we understand it, began in the Big Bang, roughly 13.8 billion years ago. It has been expanding and cooling ever since. In the early universe, roughly 380,000 years after the Big Bang, the universe became transparent to light, allowing the cosmic microwave background radiation to escape and to travel freely through space ever since. In the subsequent billions of years, gravity has acted on the tiny density fluctuations present in the early universe, causing matter to cluster into galaxies, and then into larger and larger structures. But the universe is not simply governed by gravity. In recent billions of years, dark energy has begun to play an increasingly important role in the universe's dynamics. As the universe expands, the density of matter decreases, so the strength of gravity weakens. But dark energy, it appears, remains approximately constant in strength. As a result, the influence of dark energy relative to gravity has been increasing over time. In the recent past, within the last few billion years, dark energy has become the dominant form of energy in the universe. It now drives the expansion of the universe, causing all galaxies to accelerate away from each other. Looking into the future, this trend will only continue. In the very distant future, in hundreds of billions of years or more, the universe will have expanded to such an extent that the density of ordinary matter will become negligibly small. Galaxies will be so far apart that light from one galaxy will never be able to reach another. The stars within galaxies will burn out and fade away. The universe will become a cold, dark, empty place filled with the remnants of stars, with black holes slowly evaporating through Hawking radiation, with particles slowly decaying and disappearing. Eventually, trillions of years in the future, the universe will reach a state of maximum entropy, of heat death, where no further changes are possible and nothing new can happen. But this bleak future is so distant that it contains within itself a span of time incomprehensibly vast, many times longer than the entire history of the universe to date. In the near future, on cosmological timescales, the universe will remain a place of structures, a place where galaxies continue to move through space, where stars continue to shine, where perhaps life continues to exist on some planets. The vast cosmic structures we have discussed, the superclusters and filaments and walls of galaxies, will continue to evolve slowly under the influence of gravity, but their overall character will not change dramatically for billions of years to come. And if there is life in the universe, if there are conscious beings capable of contemplating the cosmos, they will have many billions of years during which to do so. They will have time to ask questions, to develop theories, to make observations, to deepen their understanding of the universe and of their place within it. It is one of the remarkable facts of cosmic evolution that the timescales involved are such that they permit the emergence of complexity and consciousness, and that these conscious beings have eons in which to contemplate and understand the cosmos. Now let us return to the specific question that has motivated much of our discussion, the question of how the vast structures we observe could have possibly formed in the time available. We have mentioned several possible avenues of resolution, several ways that this puzzle might be solved. Let us explore these in greater depth, considering not only the technical aspects but also the philosophical implications. The first avenue of resolution we might consider involves the possibility that our measurements and observations are more accurate than we might have initially assumed, and that the structures are not quite as large as they initially appeared. This might seem to be a retreat from observation, but it is not. Rather, it is a more careful reading of the data, taking into account the statistical uncertainties and the subjective definitions involved in identifying structures. When we measure the size of a structure like the Hercules supercluster, We are not measuring something with a definite boundary, like the edge of a table or the horizon of a planet. Rather, we are identifying a region where the density of galaxies is higher than the cosmic average, and defining the boundary of the structure somewhat arbitrarily. Different definitions of the boundary will yield different measurements of the size. If we use a strict definition, considering only the regions where the density is substantially higher than average, we will measure a smaller structure. If we use a looser definition, including regions where the density is only slightly higher than average, we will measure a larger structure. By carefully choosing the definition, by using the most statistically rigorous methods available, it is possible that we might find that the structures are somewhat smaller than more casual readings of the data might suggest. This would go some way toward resolving the tension between observation and theory, though it might not entirely eliminate it. The second avenue of resolution involves modifications to our understanding of dark matter. As we have discussed, dark matter comprises the majority of the matter in the universe and plays a crucial role in structure formation. Our current understanding of dark matter is based on the assumption that it behaves as a pressureless fluid, meaning that dark matter particles do not have any internal pressure that would resist gravitational collapse. Under this assumption, dark matter can cluster quite efficiently, forming the dark matter halos within which galaxies form. But what if dark matter has properties that we have not yet fully appreciated? What if dark matter particles interact with each other in subtle ways that affect the growth of structures? Some theoretical models propose that dark matter might be self-interacting, meaning that dark matter particles can collide with each other and exchange energy. If dark matter is self-interacting, then the distribution of dark matter in structures might be different from what our current models predict. The details depend on the strength of the self-interaction. In some cases, self-interaction might actually slow down structure formation by providing a kind of effective pressure that resists gravitational collapse. But in other cases, self-interaction might affect the dynamics in ways that could potentially accelerate structure growth or allow structures to become larger than they would otherwise. This is an area of active research, with theoretical physicists and cosmologists working to understand how different kinds of dark matter might affect structure formation. New observations are also being made, with the hope of constraining the properties of dark matter more precisely and eliminating some of the possibilities. As our understanding of dark matter improves, we may find that modifications to the dark matter model can help to explain the existence of these large structures. A third avenue of resolution involves the possibility that the initial density fluctuations in the early universe were not quite as small as we currently believe. The amplitude of these initial fluctuations is constrained by observations of the cosmic microwave background, but there are still some uncertainties, particularly on the largest scales. If the initial fluctuations were somewhat larger than we currently believe, then the structures that grew from them would also be larger, and they would reach their present size more quickly. This is perhaps the most straightforward way to resolve the puzzle, at least from a theoretical perspective. But it would require us to revise our understanding of the cosmic microwave background or of the processes that generated the initial fluctuations in the early universe. A fourth avenue involves the possibility that gravity itself, on the largest scales, behaves somewhat differently than Einstein's general relativity predicts. General relativity has been tested extensively, and it agrees with observations very well on scales ranging from the solar system to galaxy clusters. But it has not been tested thoroughly on the largest cosmological scales, and it is conceivable that modifications to general relativity might be necessary on these scales. Some theoretical physicists have proposed modifications to gravity, theories such as modified Newtonian dynamics, or more exotic alternatives. If such modifications were correct, then gravity might be somewhat more efficient at causing structure growth on large scales, which could help to explain the existence of the large structures we observe. A fifth avenue involves dark energy. We know very little about dark energy, and it is possible that our models of it are incomplete or incorrect. If dark energy behaved differently in the early universe than it does today, if it varied spatially in ways we have not yet recognized, or if it interacted with dark matter or ordinary matter in subtle ways, then this could potentially affect structure formation. Some theoretical models propose that dark energy might not be the simplest form of energy, which is the constant that appears in Einstein's equations, but rather might have more complex properties. If such were the case, then the role of dark energy in cosmic structure formation might be different from what current models suggest. Each of these avenues of resolution has some theoretical merit and some basis in current physics. None of them is so exotic or so outlandish as to be completely ruled out. And it is quite possible that the true resolution involves some combination of these different approaches. Perhaps the structures are not quite as large as initial casual readings of the data suggested. Perhaps dark matter has properties that we have not yet fully appreciated. Perhaps the initial density fluctuations were somewhat larger than we thought. Perhaps gravity requires some modification on the largest scales. Perhaps dark energy is more complex than we have assumed. The interaction of all these factors might be sufficient to resolve the apparent tension between observation and theory. As we conclude our exploration of these vast cosmic structures, let us return to the larger question of what it all means, what these structures tell us about the universe and about ourselves. The universe is a cosmos, a word derived from Greek meaning order or harmony. It is not a random chaos, not a meaningless void, not a place where anything can happen with equal probability. Rather, it is governed by laws, by physical principles that operate with remarkable consistency and precision. These laws allow for the existence of structure, allow for the organization of matter and energy into galaxies and stars and planets, and eventually into life and consciousness. The vast cosmic structures we have discussed are manifestations of these laws, expressions of the fundamental principles that govern the universe. They are beautiful in their own way, beautiful in their vast scales, in their complexity, in the intricate patterns they form. And they are also mysterious, presenting us with puzzles that we have not yet fully solved, with mysteries that invite further investigation and deeper understanding. The fact that we can observe these structures, that we can measure them, that we can theorize about them, and that we are slowly but surely coming to understand them, is itself a remarkable testament to human capability and to the power of the scientific method. Through careful observation, through mathematical analysis, through bold theorizing and bold testing of those theories, we have managed to extend our understanding of the universe from the immediate neighborhood around us to the largest scales at which matter is organized. And so we find ourselves at the culmination of this exploration, standing before one of the cosmos's great mysteries, one of the riddles that the universe presents to those who seek to understand it. The existence of structures larger than theory predicts stands as a monument to both the power and the limitations of human understanding. We have achieved much. We have mapped the universe across billions of light years. We have traced the history of the cosmos back to its very beginning. We have discovered the laws that govern the behavior of matter and energy at scales ranging from the subatomic to the cosmic. But we have also discovered that there is much yet to learn, much yet to understand. The vast cosmic structures remain, in some ways, a mystery. They challenge our theories, they push the boundaries of our understanding, they invite us to think more deeply, to observe more carefully, to venture into new territories of thought and investigation. In this sense, they represent the frontier of human knowledge, the edge of what we currently understand about the universe. And it is at these frontiers, at these edges where knowledge meets mystery, that science makes its greatest discoveries and achieves its most profound insights. For science is not a collection of finished answers, a set of unchanging truths about the nature of reality. Rather, it is an ongoing process of asking questions, making observations, developing theories, testing those theories, and in the light of new evidence, revising and refining our understanding. It is a process that is no end, that will continue as long as there are conscious beings capable of wondering about the nature of the universe and motivated to investigate its mysteries. And so we are brought once more back to where we began, to those vast cosmic structures that should not exist according to our theories, that push the boundaries of our understanding, that challenge us to think in new ways, and to approach the cosmos with renewed humility. These structures are real. They exist in the universe, indifferent to our theories and our models, indifferent to whether we understand them or not. And in attempting to understand them, in striving to grasp their nature and their origin, we are engaging in one of the most human of endeavors, one of the most noble quests that conscious beings can undertake. We are seeking to understand the world in which we live, to comprehend our place within the vast cosmos, to approach ever closer to the fundamental truth of existence itself. As we look toward the future, we do so with confidence tempered by humility. We know that new discoveries await us. We know that the universe will continue to surprise and astound us. We know that mysteries remain, deep and profound mysteries, that may take generations or centuries to unravel. But we also know that through the continued application of careful observation, rigorous analysis, creative theorizing, and bold experimentation, we will continue to deepen our understanding. We will continue to expand the frontiers of human knowledge. We will continue to move closer to a comprehensive understanding of how the cosmos works, and how we fit into the grand scheme of existence. The journey of discovery is infinite, the wonders to be perceived are boundless, and the human mind, through its capacity for understanding, remains one of the most remarkable creations of the universe itself. The largest structures in the universe that should not exist are, in the end, not merely objects of scientific inquiry. They are reminders of the vastness of creation, of the intricate complexity woven into the fabric of reality, of the profound interconnections that link every part of the cosmos to every other part. They are monuments to time and to the patient work of gravity across billions of years. And they are invitations, calls to us to continue the great work of understanding, to maintain our curiosity and our sense of wonder, to approach the universe with respect and with the recognition that however much we learn, there will always be more to discover, always deeper mysteries to explore, always new vistas opening before us. In this endless quest for understanding, we participate in one of the most fundamental expressions of consciousness, one of the ways that the universe comes to know itself through the thoughts and actions of those who dwell within it. So let us embrace the mystery, celebrate the discovery, and look forward with hope and wonder to what future observations and future insights will reveal about the cosmos and about our place within it. This is the essence of science, the spirit of human inquiry, the eternal human drive to understand the universe and all its wonders.